Hello, am I audible?
Yes, sir, audible.
Okay, so let's begin. Welcome to the sixth problem solving session of the NPTEL course Design of Power Electronic Converters. The recorded lectures of the course have been taught by Professor Shabri Nath from IIT Guwahati. My name is Saleh Khan. I am a PhD student at IIT Delhi, and I will be conducting this problem solving session where we summarize the contents that were taught in the previous week and solve some problems related to those content. So for week six, it was mainly about magnetics in power electronics, which is inductors and transformers. So the we covered some fundamentals of magnetics. Then we talked about magnetic losses, conductors, magnetic materials, magnetic cores, and then an inductor design and transformer design procedure was shown using the area product method. So let's start with the some fundamentals of magnetics. So when we talk about magnetics, that is inductors and transformers in power electronics, we will usually have a magnetic core which is made of either a ferromagnetic material or some other soft magnetic material. And on this core, there are some a current carrying conductor is wound on this core with some number of turns n. And because of this current and the number of turns, it produces a magnetic field inside this core. And if we talk about the magnetic field intensity, H, using Ampere's law, we can find out what is the magnetic field intensity inside this core over the path length, the magnetic path length LC. And it is given by Ampere's law. And if we assume that in this magnetic core, the magnetic field intensity is uniform and it is parallel to this path length, then we can simplify this Ampere's law and write it as Ni, which is the product of the number of turns and the current that is uh, carried by these number of turns, is equal to the magnetic field intensity times the magnetic path length. And this product Ni is also called as the magnetomotive force MMF, denoted by F here, which we'll see can be used in magnetic circuits. So uh, using Ampere's law, once we know the current and we know the number of turns we have and the magnetic path length of the core, we can find or calculate the magnetic field intensity H, which is given in ampere turns. After we have found the magnetic field intensity, then we can find the magnetic flux density B. And this can be found by multiplying the magnetic field intensity H by a factor called the permeability of the material. So the permeability of a material of a core is the product of the permeability of free space times the relative permeability. So the permeability of a free space is a very small number in SI units, 4 pi times 10 to the power minus 7. And this basically means if we apply a magnetic field intensity uh, somewhere, how much magnetic flux density will be produced. So using the relative permeability, it basically means uh, how much more permeability does a material have compared to the permeability of free space. So this relative permeability is a dimensionless constant depending on the material, and usually it ranges from some tens to hundreds, thousands, and even more than that, 10,000s, depending on the material. So it basically uh, increases the possibility of the magnetic flux being produced inside a material. So just like in electric circuits, we have permittivity, which basically tells us how much electric current can be flown through a conductor. Similarly, in magnetic circuits, we have a related term called permeability. So these magnetic and electric circuits, they have some analogous uh, quantities that we'll see later on. So permeability is analogous to permittivity. Just like permittivity tells us that, so for example, if we have a voltage difference between 2 points, so if the voltage difference is between air, then there will be no conduction between them because it does not have a path of uh, high permittivity. Similarly, if we have a magnetic field, that magnetic field will easily flow through a material where the permeability is high. So if so, depending on how much is the permeability, then you can uh, estimate how much magnetic field can flow through that material. But a property of these magnetic materials that we have is that as we increase the H value, so ideally the B value should increase proportionally. Uh, so B should be equal to H times mu. But after a certain value of H, the relative permeability actually decreases and it becomes ultimately 1, so that all that is left is the permeability of free space, and this point is called the saturation point. And sometimes this saturation point is a very sharp point depending on the material. Sometimes it's a very gradual process, but in all the materials that we have, the magnetic materials, we usually encounter this saturation phenomenon somewhere, so that the permeability of the material after a certain value of permittivity, it will decrease. So once we have found the uh, magnetic field flux density, we can find the magnetic flux from that using the cross-sectional area of the core. So it is shown here. So if this is a core, the cross-sectional area of the core, when multiplied by the uh, magnetic flux density, and if we assume that the flux density is uniform and it is perpendicular to this core area, cross-sectional area, then we can find the magnetic flux inside the core. And the core will also have the flux will have a direction depending on the direction of the current, and then you can apply a right hand rule and you can find what will be the direction of the flux. For example, in this case, if you see that the current is flowing to the back, so if you see from the winding, the front portion of the winding, the current is flowing towards left, and if you apply the right hand rule, then the flux will be from top to bottom. It will be in the downward direction uh, in the winding, and overall it will be in the anti-clockwise direction. So that from the magnetic flux density, you can find the magnetic flux. And lastly, from the flux, we can find the flux linkage. So basically, if this flux flows through the entire core, that means it flows through all the number of turns, n turns, then all the n turns are linked by this flux. And then we can find the flux linkage by multiplying the magnetic flux times the number of turns n. And this quantity can be is a fundamental quantity uh, in magnetic circuits, and when it changes, then we can produce a voltage, as we will see later on. But now the flux linkage can be directly related to the current. If you see all these factors, I times n by Lc times mu times Ac times n, we can find uh, the magnetic flux linkage from the current. And this multiplication factor is called the inductance of the particular arrangement of the core and the windings. And this inductance, if you just multiply all these terms that we have, it will be given by n square divided by the magnetic path length divided by mu times the cross-sectional area of the core. And this denominator is actually a quantity called the reluctance of this magnetic circuit. Uh, so basically, by multiplying the current with this inductance value, we can find the flux linkage. And as you see, this flux inductance value, it determines, it is uh, basically it depends on the geometry, which is the LC and AC of the core, and the material, which is the mu factor, and then how many turns you have wound. And then we can vary the current, and then we can get different values of flux linkage. But for a given inductor, the value of the inductance, if all these terms remain constant, if the number of turns remain the same, if the path length remains the same, if the core cross-sectional area and permeability remains same, then the inductance will remain same. So now uh, we can find, uh, now we have a law that is called the Faraday's law. It basically tells us that if this flux linkage changes, then a voltage is induced in that winding. So the flux linkage that is linked in the winding, if it changes, then a voltage will be produced which will be equal to the derivative of this flux linkage. And then we can uh, basically write it as different, uh, in different ways. We can write it as n times the change in the flux, or we can write it as L times the change in the current from the equations that we saw previously. And we can find the polarity of this voltage using Lenz's law, which says that so once a voltage is produced or induced in the coil, and if we complete the circuit through some other components, then a current will flow in that circuit due to this induced voltage. And the Lenz's law states that the induced current will produce its own field, magnetic field, and that field is in such a direction that it opposes the changes in the initial magnetic field. So we have an initial magnetic field, and that initial magnetic field is changing. It will produce a voltage, and that voltage will lead to a current, which in turn will lead to the second magnetic field. And the direction of the second magnetic field will be such that it will oppose the change in the initial magnetic field. And from that, we can basically find what will be the direction of the induced voltage. So next we can, so if this magnetic uh, arrangement that we have of the core and the winding, we can then uh, understand it or analyze it in what is called a magnetic circuit. And this is analogous to the electrical circuit. In here, the voltage is replaced by the MMF that we talked about, which is the product of the number of turns and the current. The current is replaced by the magnetic flux, and the resistance is replaced by reluctance, which we said is the ratio of the magnetic path length and the product of permeability and the cross-sectional area of the core. So then it will, this magnetic circuit, we can solve it just like electrical circuits. We can apply KVL, KCL. So uh, basically, Ni will be equal to phi times R, that is the KVL. And if we have multiple branches here, then we can apply KCL as well, where the entire phi will be divided into multiple fluxes. So magnetic circuits, they will behave just like electrical circuits, and only you have to make the analogous changes. Now, this magnetic flux, it will depend on the reluctance. So if you see that, if you understand the magnetic flux is just like the current in the electrical circuit, then this current will be given by the MMF divided by the reluctance. And if we want to now control this flux value, uh, we can control it by either changing the number of turns or the current. But if this MMF is fixed, for example, for some reason that the number of turns is fixed and a particular current is passing, and the core uh, the core size is also fixed, size and material is also fixed, like LC, mu, and AC are fixed, then how can we determine or control this flux? This is done by introducing what is called an air gap. So that means if we have the core In the path of the magnetic field, we will remove the core, some portion of the core, so that only air remains in that portion. And it is done in such a way that this length Lg of the air gap is much smaller than the length Lc of the magnetic field. Uh, so in that, then we can basically, then this circuit will have two reluctances. One will be the reluctance of the core, which will be much less than the reluctance of the air gap, because as we saw, the formula for reluctance is Lc divided by mu Ac, and mu has the relative permeability factor times the permeability of free space, and that mu r can be thousands. It can have a value of in the range of thousands. So that is why the magnetic reluctance of the core will be much smaller than the reluctance of the air gap. And in fact, this air gap will determine the reluctance of the whole circuit, whole magnetic circuit, and then it will also determine the flux that will pass through the circuit. So LRG will be given by Lg, which is the length of this air gap, divided by mu naught or mu zero, which is the permeability of free space, which is much smaller than the permeability of this magnetic material. And then we can find RC as well if we, like I said, that Lg is much smaller than Lc. So we can approximate it like this. And basically, uh, if the length Lg is much smaller than Lc and the relative permeability is much higher than the permeability of free space, then the inductance will basically be determined by the air gap uh, length or air gap reluctance only. And we can approximate the inductance as n squared divided by Rg in that case. So this air gap allows us to control the flux and in turn control the inductance as well. Now, after these fundamentals we have covered, now we can talk about some losses that occur in magnetic circuits. So just like we saw in semiconductors, we had different types of losses. We had switching losses, conduction losses. Similarly, in magnetic circuits, we can have different types of losses. We can have losses in the winding of uh, the inductor or transformer, and we can have losses in the core material. So in the core, we can have two types of losses. One is called the hysteresis losses, and another is called eddy current losses. So hysteresis, you may have read before that. Uh, so what we saw previously, the BH curve, where for a particular H we got a particular value of magnetic flux density B. In practice, what happens is that uh, it is not a linear straight line, but not only does it have saturation, but it also has different values depending on whether the H is increasing or decreasing. So if we start from zero, then we go to some value, peak value, and then if we reduce H again, it will, when H becomes zero, uh, then B will not be zero, B will be some negative value. Similarly, when it goes negative and then it goes again to zero, then B will have some positive value. So it does not follow a linear straight line, but it follows this kind of a curve. And because of this, there are some losses. Because if you uh, find that the area of this, it will have associated losses with it. These are called hysteresis losses. And then because it is a magnetic field that is uh, produced inside this material, core material, and we know that a magnetic field can produce an electric current. And depending on the resistivity of the core material, this electric current can have uh, different values, and it will have associated losses with it, the I square losses of the eddy current. And that is why another source of core loss is called the eddy current losses. And both of these losses, the hysteresis losses and the eddy current losses, they happen inside the core material, and they will lead to heating up of the core material. And there are different methods how to calculate or find out these losses. Uh, a simple method is what is called the Steinmetz equation, where the core loss density, which is the core loss per unit volume, is given by this equation, where K, uh, M, and N, these are uh, constants that are given by the manufacturer of the core material. So for a particular material, these values will be fixed, and then F is the frequency. So basically, whenever we traverse this hysteresis loop, we get some losses. And frequency basically means how fast are we traversing this hysteresis loop. So if we increase the frequency, then we will get more losses. And similarly, BM is basically the peak of the loop that we have. From 0 to BM will be the peak. So based on that, if you go to a very high value of flux density, then your losses will also increase. Compared to if you have a very low BM value, that is the peak value, then the area will be less, and then the hysteresis losses will also be less. So uh, this is a one of the formulas that can be used for core losses. And if you want a more accurate picture or a more accurate value, and it also depends on what is uh, the shape of the variation in B. So if it is a sinusoidal variation, then this Steinmetz equation is it gives a good approximate of the core loss. But if it's not a sinusoidal variation in B, then uh, there are some other equations that can give better approximation of the core loss. But here we will only stick with this equation, uh, and we can calculate the core loss using this equation. And this PC value will be the core loss per unit volume, and then you have to multiply that with your particular volume of the core. And the volume of the core is, in this case, we are talking about the volume which is the product of the path length LC and the core cross-sectional area AC. And that is what we mean by the volume of the core for this case. So next we have the winding losses. The winding losses can be due to DC resistance and AC resistance. So DC resistance is simply what you understand by resistance of a wire, or the resistance of a winding. It is given by the resistivity times the length divided by the cross-sectional area of the wire, and this will be the DC resistance of the winding. But due to some skin and proximity effects that I will not go into right now, you can check the lecture one lecture in the course if you want to find more details about the skin and proximity effects. But it basically increases the overall resistance uh, of the winding, but only for AC currents. This skin effect and proximity effects, they happen because of the change in the currents, and they only happen due to the AC portion of the current. So that is why it is called an AC resistance, and it is usually uh, higher than the DC resistance by a factor, which here is given by FR. And then we can find the losses related to the DC portion of the current, which will be given by IDC square times the DC resistance. And then we can also find the losses related to the AC portion of the current, which will be given by the RMS of the AC portion times the AC resistance. But here we will only focus on the DC resistance portion. So next, now the conductors that we have here, they will be slightly different than the normal conductors that are connecting some portion in the circuit. So if you want to connect a resistance to the circuit, you will use a different wire compared to what we have uh, in inductors and transformers. We can have different kinds of wires. One is a single strand wire, which is basically something like this, where you have a single metallic strand discovered by some insulation. And then we can also have a multi-strand wire, which is shown here. So a multi-strand wire basically means it will have different multiple strands of copper wire, and they will be bunched together, and then one insulation will be around that bunch of wire. And this basically the reason why we make a stranded wire is that if the size of the wire becomes very large, then it becomes very difficult to uh, make turns in a single stranded wire because it becomes very hard. So that is why we have this multi-strand wire where so it becomes easier to wind the wire and change basically bend the wire in some portions. But if you see this stranded wire, these are all copper wires and they are in touch with each other. So they will be basically not insulated from each other. They will be in electrical connection with each other. So, and then we have what is called a Litz wire, which is also a multi-strand wire, but the difference compared to the normal standard wire is that it has multiple strands and each of these strands is insulated from each other. And this kind of a system is used to reduce the skin and proximity effects, or at least the skin effect, because these uh, all these wires are insulated from each other, so uh, it does not allow the skin depth will be limited to each individual strand, and the strand itself can be very small so that the skin effect will be negligible in each strand, and then we can reduce the AC resistance of the wire using this kind of a Litz wire system. Now, how to choose a wire depends on the size of the wire. So the wire gauge, different wire gauges are given. So for example, AWG is the American wire gauge system. We have other systems as well, like SWG, which is called a standard wire gauge or some other system. And in these systems, basically, uh, different uh, labels are given to different wires. So for example, AWG 40 will be a very small wire. It will have a very small diameter and it will have a associated cross-sectional area, and then it will have a resistance per length of that wire. And for very if the AWG is very high, then the diameter is small, area is small, and resistance is high. Resistance per unit length is high. And as we reduce the AWG, then the wires become very thicker, and that means the current carrying capacity will increase, the diameter of the wire will increase, the area of cross section will increase, and therefore the resistance per unit length will decrease. So depending on how much current you want to carry in your inductor, you will choose an AWG accordingly. And we don't want to choose a very low AWG because then it will be a very large cross section of area of the wire, and we will only choose what is enough for the current to be sustained. So for example, if we require a wire area which is corresponding to AWG 30, then we can choose around that value 30, maybe 29, 28, but we will not choose a value AWG 10 because uh, it will be basically not suitable. It will be the wire will be too large. It will take too much space in the inductor. We will require a very large inductor unnecessarily. So that is why we can, if you want to optimize your design so that it becomes and the inductor becomes as small as possible, then you can choose a very appropriate AWG wire of your gauge. So next, there are different types of magnetic materials that I cannot go into right now because the time is limited. But I'll just talk about what are some desirable characteristics of the magnetic materials. So firstly, the magnetic material should have high relative permeability so that all the flux is so it will provide a very low reluctance path to the flux so that the flux will be contained inside the magnetic core, and then it will allow us basically can possibly allow us for a smaller size of the inductor or transformer. Next, it should have high saturation flux density so that we can go to higher values of H without the core getting saturated. So if the core gets saturated, then uh, its inductance will decrease because the mu will decrease and inductance is sort of related to the mu. So if we want a particular inductance and if we want, then we should have high saturation flux density. Otherwise, uh, we will have to use a larger core. It should have high electrical resistivity. So this means that uh, the resistivity of the core material, so we are not talking about the wire, but the core material should be high so that the eddy currents will be limited. Because of the resistivity and therefore the resistance of the core, electrical resistance of the core is high, then the eddy current will be limited and therefore the core losses will be limited. Next, we have high Curie temperature, and is basically means that at a certain temperature, the magnetic material stops behaving like a magnetic material, so its uh, permeability will reduce. And that temperature, it depends on the material itself. So we want to have a very high Curie temperature so that even if there are losses, the temperature of the core will increase. It should not go near the Curie temperature, otherwise we'll lose the magnetic properties. Next, the magnetic material should have low core loss density so that obviously the losses are reduced. So we can have higher efficiency and also the uh, temperature rise, because in power electronics, when we talk about low losses, we have two targets in mind. One target is that the efficiency should be high, and that is obviously a good target to have. But sometimes it is more important that the losses associated with it, they have a heat. Uh, the losses basically they are dissipated as heat, and the heat increases the temperature, and that temperature rise can damage the device. For example, it can go near the Curie temperature, so it will stop behaving like an inductor. If it is a product that will be is to be handled like a phone charger, and if it goes too high in temperature, then the user will be basically, it can hurt the user. So that is why when we talk about reducing the losses, we have in mind the efficiency as well as we have in mind the temperature rise in the component that we are talking about. And lastly, we will want to have a high maximum frequency. And again, this is related to the losses as well. If we have if the core losses are high, then we cannot go to very high frequencies because as we saw that core losses increase with frequency. So the magnetic material should have high maximum frequency, or at least the frequency that we want to operate the inductor or transformer in. The magnetic material should allow that kind of a frequency. Now, magnetic cores, there are many geometries that are available. There's some that were shown in the cores like toroidal cores, E cores, U cores, ETD, and pot cores, and all those cores, and they have their own positives and negatives. And depending on the application, you have to see which kind of a core is available. Uh, and once you select a core, you will be given two kinds of data. One is the dimensional data. For example, here I've shown an ETD core. It is called ETD because it looks like an E, like the letter E of the English alphabet, and this middle leg is a circular instead of a rectangular. So it is called ETD, and the dimensional data that will be given will be basically related to the dimensions of all these lengths. The lengths that are shown here, they will be given in the by the manufacturer, and then the design data will be what is shown in the second table. It can be about the weight of the core. It will be the mean length per turn, and I'll explain it later on what is this mean length of turn. And it can be the mean path length, which is the magnetic path length of the core. They will also give us the cross-sectional area of the core, the window area, which is basically this area, window area. They will give the area product, the kg factor, the surface area, and all these terms will be used later on for analysis purposes. And even if these values are not given, you can actually find it from the dimensional data. The dimensional data is necessary. It must be given by the manufacturer. But even if these design data is not given, you can find out. So, for example, the AC, if you know the E term, you know the E term, which will be the diameter of this middle leg. Then, if you know the diameter, you can find the area AC. Similarly, if you know the length G and uh, B and E, then you can find the window area. Uh, there will be formulas for the uh, there'll be formulas for the surface area, the mean path length. On all these can be found out from the dimensional data. But sometimes uh, these design data is also given by the manufacturer. At least the magnetic path length as well as the core cross-sectional area. These two are usually given by the manufacturer. Uh, Next, we have in magnetic cores what is called window utilization. So, for example, here I've shown an EE core, which means this core has two parts, and both of them they look like the letter E, and they have to be connected together to make the full core. And once we have this core, and if you want to wind the wires inside this core, before we wind it, we have to use what is called a bobbin. So it is shown here, this white colored portion. This bobbin, we wind the wires on this bobbin, and then this bobbin is inserted in the core. And as you can see, this bobbin will take up some space inside the winding area or the window area. So this WA is the window area, is shown in this light blue. The bobbin will take some area. Then we have the wires, and the individual wires will have insulation around them. And then they have to be, if you want to have some number of turns, then they will be wound together. And as you can see, there will be some spaces left between these turns. And then ultimately we cannot, so for example, if we have the wire area is given, and then some portion will be left again unused. So because of all these reasons, because of the presence of the bobbin, because of the insulation, the the space that is left between the wires when we wind the wires, because of all these reasons, uh, the entire area of this window cannot be utilized by uh, the copper portion of the wire. So the ratio of the copper portion of the wire to the full window area is called the window utilization factor, or sometimes called the fill factor. And this you can find out by number of turns n times the individual area of the copper. So we're talking about the copper area and not the full area of including the insulation. And then we divide it by the window area, we will get the window utilization. And because of these factors that we talked about, the bobbin, the spacing, the insulation, usually the window utilization is kept between zero point 0.4 or zero point 0.5. So 40 to 50% of the area is utilized. And if you utilize a higher area, then means basically uh, a lot of this window area will be covered by the winding, and that means your inductor size can be small, because if the if the window utilization factor is less, that means some portion of the window is unutilized, and that means you are using a larger core uh, when you could have used a smaller core. So we want to have a high window utilization factor, but because of these limitations, we cannot go beyond a certain value. If zero point 0.5, zero point 0.6 will be very difficult because of the presence of the bobbin and the spacing between them. So now we can come to what is called the area product. And area product is basically the product of this window area and the cross-sectional area of the core. because these are two areas. When we multiply them together, we get the area product AP. And area product, as we'll see, is related to the energy that is stored in the inductor, as well as the window utilization factor, the current density, and the working flux. So if we to derive that, we can basically see that if the flux linkage is given by the inductance, or the peak flux linkage will be given by the inductance times the maximum current or the peak current. And we saw that this can also be written as n times the number of turns times the flux, the peak flux in the core. And then the flux can be written as the peak flux density times the core cross-sectional area. Then we can substitute for this number of turns using the formula that we saw just in the previous slide for the utilization factor. And once we substitute n, we get this equation at the which is shown at the bottom. Now here we can also eliminate the wire area by if we understand that the the current will be flowing through this wire area, and then we will get a particular current density. Current density J will be given by the peak current divided by the wire area, and then we can use this expression to substitute AW in our original expression. So we will get this equation for L times Imax, and if we rearrange this equation, we can find the area product, which is the window area times the cross-sectional area of the core. It will be given by L Imax square divided by the Ku, which is we talked about the utilization factor, times B peak, which will be the peak flux density, and times uh, the current density inside the winding. And the numerator of this is actually twice the energy that is stored inside the inductor. The energy that is stored in the inductor is given by half Li square. So twice of this will be Li square. So the area product is actually related to the energy that is stored. Uh, so that means if, and we know that area product is basically a product of these two areas, which depends on the geometry of the core. So if we select a particular core geometry, that means we it will limit the peak energy that can be stored in that core for a particular value of this Ku, B peak, and Jm. So uh, so once we have a particular application, we can find and we can specify what will be a Ku, what will be the B peak and Jm. And if we know the what is the inductance required and the current, we can find the area product, and then we can look at the area product of different cores, and then we can choose our core accordingly. So now the steps for inductor design using this area product method is that first of all, we will have some design specifications. So we will have two kinds of specifications. One will be related to the converter. So for example, we have a particular inductance that we require. This can be from if we want to limit our inductor ripple to a particular value, if we want to limit THD in case of grid connected applications, or some other reason, we will have chosen the value of inductance. We will also have an average inductor current depending on the power level. We will have the inductor current ripple delta I. We will have a particular output power, and we will have switching frequency. So all these are related to your converter. Then we have to choose a particular current density. So in this area product method, we have to choose a particular current density, and like this, you can choose as 3 to 5 amperes per mm square. Usually, that is the current density that is chosen, and sometimes it will be given to you in the question or in the application that this is the current density we can go up to. We can also have an operating flux density. So this will be usually slightly lower than the saturation flux density of the material, because we want to use the material as much as possible. So we will go very close to the saturation, but not exactly to the saturation. We will have some room for in case of there is a transient, so that the flux density goes higher than our operating flux density. So it will be uh, close to but smaller than the saturation flux density. And that will also depend on the core material. So we have to choose a core material beforehand. And then we'll choose a utilization factor. It can be between zero point 0.4 to zero point 0.5, as I said. And then we'll have a temperature rise. So this temperature rise, as I mentioned previously, it can be based on the Curie temperature. So we should have the temperature should not go beyond the Curie temperature. It can also be so the insulation does not melt. So it should be the melting temperature of the insulation. Or it can also be if it's a product that has to be handled by the user. So it should be the temperature rise should be low enough so it should not harm the user. So all these things, it depends on your application, but usually you will be given a temperature rise. So if your maximum ambient can go up to 40 degrees, you will be given a temperature rise, let's say 30 to 50 degrees. You cannot go beyond this temperature rise. And these are the specifications that you will be given. So once we have these specifications, we have to calculate the area product. So that is this formula that we've shown. It's uh, Li peak square divided by the Ku. So L we know, L peak we can find out, IL peak we can find out by the average current plus half of the ripple. Ku we have specified, the working flux density will have specified, and the current density also we have specified. So once we find the area product, next we have to choose a core. So once we have chosen a material, and we have if we even we have to choose a shape first, and then we will have this kind of a table given by the manufacturer. Different manufacturer can they will give different names to their cores, and then we have to match the area product. So the area product of the core that we chose, it should be uh, equal or slightly higher than the area product that we get from our calculations. It should be higher. It should, if it is lower, then that means that core can not handle this much energy. So that is why usually it should be equal or slightly higher than the calculated value. And once we have chosen the core, we have to select the wire. And the wire gauge will be selected based on the area of the wire. And the area we can calculate based on the RMS current divided by the current density. So we will get a particular value of uh, uh, wire of the area, and then we can look at the AWG table. Again, we will choose a wire whose area is equal or slightly higher than the area that we got here, so that the the current density will be either equal to this Jm value or it will be less than. We don't want to go beyond this value because this is the specification that we are given. And once we match the uh, area of the wire, you have then you'll get the AWG number. And that particular wire will have a particular area, it will a cross-sectional area, it will have a particular diameter, and it will have a particular resistance per length. So all these things will be selected once we select the uh, area AWG. And next we have to calculate the number of turns. Again, we will use the utilization factor formula. So we know the utilization factor. Once we have selected the core, we will also know the window area. And once we have selected the wire, then the area of the bare wire will be fixed. So then we can find the number of turns that are required for the inductor uh, to be made. And lastly, we can calculate an air gap, whether it is required or not, because we want to have a particular inductance. We have chosen a number of turns, And then we should have the reluctance in such a way that we get this particular value of inductance. And if you substitute the value, the expression for the reluctance of the core and the reluctance of the air gap, then you will basically get the length of the air gap as this expression here. It depends on the number of turns, it depends on the cross-sectional area of the core, the inductance required, the magnetic path length, and the relative permeability of the core material. So once all these things are done, then basically you have designed the inductor, because you have selected the core, the wire, the number of turns, and the air gap. Then the inductor is basically designed. But before you have to actually check some design specifications are met or not. So the first design check is you have to see what is the operating flux density and what is the peak flux density. It should be less than the saturation flux density, and the operating flux density should be what is required. So basically, you will have, for example, in a buck converter, you can have a current like this. And that means if the core has a particular BH curve, uh, but with this kind of a current, you will not follow the entire BH curve. You will have uh, a DC value of the current. The DC value of current will produce a particular DC value of field intensity, and that will lead to a DC value of the flux density, BDC. And then on top of that DC value of flux density, you will have an AC value of flux density, and that will be related to uh, the current ripple in the inductor. And from the DC value to the peak will be BM, and that is related to the core loss. And then BDC plus BM will give us the peak uh, flux density, and that should be less than uh, the saturation flux density of the core material. And we can find the expression for the flux density using these steps that have shown. So we start with basically the Ampere's law. Uh, the MMF Ni is equal to, in this case, we have a core material and the air gap. So we'll have these two terms here, the field intensity inside the core times the magnetic path length, plus the field intensity in the air gap times the length of the air gap. And then H, we can, H is equal to B divided by mu, and then we can substitute here. And here we are assuming that the flux density inside the core is equal to the flux density inside the air gap. And this is valid because the air gap is small, so we assume there is no what is called fringing is happening. So this we can assume, and then we can find the value of BC by rearranging this second equation. It will be given by the last expression that is shown here. And this flux density is for a particular current I. Now, if you want to find the flux density related to the AC portion, or which will give us the loss, the core loss, then we can find Bm by substituting delta I by 2 in for I. And if we want to find the peak value of the flux density, then we'll substitute IDC plus delta I by 2, where the I term is here. So in this way, we can find different flux densities, whether the AC portion of the flux and well as the peak value of the flux density. Next, we can find the power loss and as well as the temperature rise. The power loss, there will be two terms. First is the core loss, which will be given by, as I showed previously, the Steinmetz equation. It will be related to the uh, it will be related to the switching frequency, or the frequency with which the flux density changes, as well as the AC portion of the flux, and the volume of the core, which, as I mentioned, it is equal to the path length times the cross-sectional area. And then we can find the winding loss as I square RMS times the the resistance of the wire. And the resistance of the wire, now we know the resistance per length of the wire from the AWG table. So now then we need to know what is the length of the wire. The length of the wire will be the number of turns times the mean length per turn. So for example, if we have a uh, an arrangement that is shown here, the first layer of the winding will have a particular length of the turn. Because a turn, for example, if it starts from this point, it will go around the core limb and then it will come back. So this all this portion of wire, it will have particular length, and all of the turns in the first layer of this winding, they will have the same length of each turn. But for the next layer, the length of the turn will increase because now it has to cover a larger circumference uh, when it makes the turn. Similarly, in the third layer of winding, the length of the turn will increase even further. So, so if the for the layers that are closer to the limb, to the basic the middle limb, the length of the turn will be smaller, and as we increase the number of layers, the length of the turn will increase. That is why the manufacturers, they will sometimes give the mean length of the turn. So it will be a length of the turn, which is basically a mean of all these layers. So it will be basically the length that is from the middle portion of this the core, and it will be given in the data of the core. And once you know this mean length of the turn, you can multiply it by the number of turns and then the resistance of the winding per unit length. So you will get the resistance of your overall winding. You can find the winding loss. And once we find the total loss, which is the sum of the core loss and the winding loss, we can find the temperature rise using this expression. This is an empirical based expression. So people have measured the temperature rise for different losses, and then they have curve fitted this kind of an expression. And this expression basically depends on the total core loss and the uh, surface area of the core. And you can understand that if the surface area increases, then you have more surface for the heat to dissipate. That means your temperature rise will be less. So that is why this AT is in the denominator of this term. And if your surface area decreases, so that means for the same loss, it is happening inside a smaller surface area, so it has less area to dissipate, then your temperature rise will increase. Similarly, the total loss is in the numerator, so that if you have more loss, then the temperature rise will be higher. So this you can find used to find the temperature rise. And this temperature rise should be within the limits. Similarly, the flux density should be within the limits. And if it happens that the rise is not within the limits, then you have to choose a larger core. A larger core will have a larger uh, uh, surface area, and other things will also change. So it may be possible that the overall loss as well decreases. But usually for a larger core, the temperature rise will then be smaller so that it can fit into your limits. So these design checks are done at the end of your after you choose the core. And if the design checks are passed, then that core is sufficient. If they are not passed, then you have to choose a different core, maybe a larger core or something like that, or maybe even the material may not be enough. So this is the design. Uh, these are the design steps for designing an inductor. I will not go into the transformer because the time is limited. Uh, and maybe if I get time, I can do a summary in the uh, next week session. But for this week and the assignments, you are basically limited to the inductor portion. So now we can begin some problem solving where we have to actually select a core and see all these how this actually works. And so we have to design an inductor for a boost converter. The value of the inductance is given as 60 micro, and the current rating is also given. So we have an average current of 18 amperes. The ripple is given as uh, zero point 0.4 amperes. So, so these were the converter specifications that I was talking about. And then we are also told the working flux density is zero point 0.2 Tesla. The current density should be 3 amperes per mm square, and the window fill factor is zero point 0.4, which is 40% basically. So now the problems we can, before we solve the problem, we can actually have a short break. So after the break, we will continue with the problems related to designing this inductor. So it is 4:06 right now. We can have 5 minutes. So uh, 4:12 we'll resume again. Okay. So we'll continue at 4:12. Okay, so let's continue. So as I mentioned, we are given the specifications. The converter specifications are basically the inductor is 60 microhenry, the DC current is 18 amperes, the AC current is, or the ripple portion is zero point 0.4 amperes, and then the specifications are given that the working flux density has to be zero point 0.2 Tesla, the current density has to be 3 amperes per mm square, and the window fill factor has to be zero point 0.4. So the first question is that we have to find the area product. So we have to use this formula, which is L I peak IL peak square divided by the Ku times Bm times Jm. So before that, we have to find the IL peak, which will be given by the uh, DC current plus half of the AC current. DC current is 18 amperes, AC, the ripple is zero point 0.4 amperes, so the peak current will be 18.2 amperes. And then we find the area product, and you have to be careful here. You have to use the SI units first. So be careful about the units. Ultimately, you have to write it in centimeter raised to the power 4, which is basically square of the area. Uh, but it would be good if you find it in SI units first. So L is 60 micro, which is a 10 to the power minus 6. Ku is zero point 0.4, Bm is zero point 0.2 Tesla, which is already in SI units, but Jm was given as 3 ampere per mm square. So just you have to translate that mm into uh, meter square, and then you find the area product, which will be in this case is equal to 8.281 times 10 to the minus 8 meter raised to the fourth power. And then if you convert it into centimeter, you get 8.28 centimeter raised to the fourth power. So the answer is 8.28. Uh, be careful about the units in this case. Next, we are told that we have to choose an EE ferrite core. So the data was given in the lectures. You have to choose the part number. So based on the area product. Uh, yeah, the SI units basically for inductance is in henries. So we are given the value as 60 microhenry. So that is why I used this 10 to the power minus 6 product here. So now this L becomes Henry. The current is already in amperes, so that is fine. Ku is dimensionless, so it is zero point 0.4. Bm is zero point 0.2 Tesla, so Tesla is already SI unit. And then current density is given in 3 amperes per millimeter square. You have to convert it into 3 amperes, in amperes per meter square. So that will give you 3 times 10 to the 6 amperes per meter square. So then it becomes SI units. So then you get the answer in terms of meters. Uh, and then you have to translate it back into centimeter. So all the terms that you have here, you keep them in SI units. For the inductance, the SI unit is Henry. So you are given in the question gives us in microhenry or millihenry, depending on whatever you have, you convert it into Henry first. The current is usually in amperes, but if you have, for some reason, if it is in milliamperes, so you have to convert it into amperes first. Uh, Ku is dimensionless, so it will be in whatever value you are given. You use that value, whether it is 0.4 or 0.5. Then Bm is in Tesla, which is the SI unit. So if it is given in millitesla or some other CGS value, you have to first convert it into Tesla. Okay, if you are given in some other unit, you can find online what is the conversion uh, factor, but ultimately you should uh, get it in Tesla. And finally, current density. So current density is amperes current per unit length. So for current, the SI unit is amperes, and length, the SI unit is meters. So you should get uh, current per, you should get amperes per unit meter, per meter square, sorry. So you are given here 3 amperes per mm square. So I will convert it into amperes per meter square. So what I get is 3 times 10 to the 6 in that case. And then I get the area product in terms of meter to the power, the fourth power. And then I can convert it back to the centimeter. That is what is asked in the question. So the question is asking for a particular unit. So that is, I will convert it back into that unit. So the area product that we get is 8.28 in terms of centimeter to the fourth power. So now we have to choose the core. So we have to use the data that was shown in the course lectures for EE course. So if you go to the lectures, you will find this table, and we have to the area product that we got from the calculation was 8.28. So the core we have to choose should have an area product that is equal or slightly higher than this. And if we see the cores, and they are in order of increasing area products. So the first core that satisfies this area product is the last one that is shown here, EE75. So before this, the area core, the core was EE625, but in this case, the area product is only 4.5. So this is also in centimeter to the fourth power. So the unit is same. So, but 4.5 is less than 8.28. So this core is not sufficient. So we go to the next one, and next one is 9.4. So that is higher than what is our requirement, so that we can use. So this is the smallest core in this list that we can use. So the answer to this one is EE-75. So that is the core that we can choose, the EE core. And then we can use this table to get the other design data. So for example, then we are asked for the cross-sectional area in centimeter square, and the magnetic path length in centimeter, and the window area in centimeter square. And again, we use the same table. We can see that the cross-sectional area AC is 3.37 centimeter square. The mean magnetic path length is 10.7 centimeter, and the window area is given as 2.799, and if we round it up to 2 decimal places, we get 2.8 centimeters square. So based on this table, you can find the answers to all these design data questions. And next, we are told to calculate the RMS current. So for the boost converter, we know how the current looks like. It has a triangular shape. It has a DC portion and then triangular AC portion. And what was taught in the lectures, and uh, it was also mentioned in one of the previous sessions, the RMS for this kind of a current is given by the square root of the square root of the square of the DC portion plus the square of the AC portion divided by 12. And in this case, since the AC ripple is very small, it is only 0.4 amperes. If you uh, do this calculation, you get that the RMS current is 18.0004. And if we approximate it up to 2 decimal places, we get basically 18 amperes. So the RMS is almost equal to the DC because the AC ripple is very small. So once we have the RMS, we can find the cross-sectional area because we have selected the current density is already given in the question. So the cross-sectional area we have to find in mm square. Again, you have to be careful of the units. So because the current density was already given in mm square, 3 amperes per mm square, so I did not convert it into SI first. I just used it directly. So it is 18 ampere RMS divided by 3 ampere per mm square. So I will get the cross-sectional area of the conductor as 6 square. So this is based on the RMS current as well as the current density that was already given in the specifications. So now once we have the area, cross-sectional area of the conductor, so that is the individual wire, we have the cross-sectional area, then we can choose an AWG. So again, we can see the data that was given in the lectures. And if we again the cross-sectional area that we got was 6 square, and we have to choose a wire gauge which has slightly greater, equal or slightly greater than this value. And uh, so basically, if the AWG is less, then the area will be high, and as the AWG increases, the area decreases. So if I see this AWG 12, its area is only 3.3 square, but I need 6. So I have to go to lesser AWG. And the first AWG that satisfies this condition is AWG 9, because AWG 10 has area which is less than 6, and AWG 9 has an area which is slightly greater than 6, is exactly 6.63 square. So the answer to this question is AWG 9. Okay, so I hope that is clear. The AWG has to satisfy the area condition, and it is satisfied by AWG 9. So it basically means we can use all the AWGs 9 and above, or 9 and below this. So it is given in the table above this 9 value. So we can use AWG 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. But for all other than 9, the the diameter of the wire will become too much, so it will take more space in the window, and it will take unnecessary space in the window. So that is why we will only select AWG 9. Okay, someone is asking to repeat three questions 3, 4, and 5. So 3, 4, and 5 are basically we have to find the cross-sectional area, the magnetic path length, and the window area of the core that we have selected in the previous one. Okay, so the second question was basically we are asked to choose a core. So in the first problem, we found out the area product, which came out to be 8.28 centimeter to the fourth power. Now we have to choose an EE ferrite cores based on the data that was given in the lectures. So this is the data that was given in the lectures. Uh, so you can just see the lectures and you can pause at the relevant portion. This is the data that was given. So we have to choose a core whose area product is equal to or slightly higher than this value that we got from the solving the first problem. And if you see the area product, this is the column of the area product in centimeter to the fourth power. And the first core that satisfies this condition is EE75, EE-75. And basically, if the core goes greater than this size, then the area product will also increase, but that will be too much. So the core that we have to select is only EE75 because this core satisfies our condition. Okay, so I hope that is clear. We select the core based on the area product that we calculated. The core should have an area product that is equal to or slightly higher than what we got in our calculations. And next, these problems are basically asking, once we have selected the core, we have to then find out the cross-sectional area, the path length, and the window area. And again, we can use the same table that we saw. This table gives all these values. It gives the area, cross-sectional area as AC, so it is 3.37. It also gives the magnetic path length in centimeter, which is 10.7, and the window area it also gives as 2.799, which if you uh, round off to the two decimal places, you get 2.80. So I hope that is clear. Uh, these are just design data you have to see from the table. Centimeter is the unit that you have to give these values in. So the magnetic path length, so you can write it as 10 centimeter, you can write it as 100 millimeter, you can also write it in as zero point 0.1 meter. But the question is specifically asking about centimeter, and cm2 is basically centimeter square. So uh, the 2 has to be in superscript in these cases. So centimeter is the length and centimeter square is the area, is the unit of the area. So centimeter and centimeter square are not the same. Centimeter is the unit of length and centimeter square is the unit of area, because cross-sectional area and window area, these are areas, whereas path length is just a simple length. So I hope that is clarified. The RMS current we already found using this expression. Cross-sectional area, again, we found from the RMS current and the current density that is given in the question. And then we selected an AWG based on the wire cross-sectional area. We got an area of 6 mm. So that is why we selected an AWG which is slightly higher than 6 mm, 6 mm square. So we selected AWG 9. And next we have to calculate the number of turns. So basically we use the uh, utilization factor formula. We know the utilization factor has to be 0.4. The window area we already saw from the core data. It is 2.8 centimeter square. So again, I converted into uh, I converted into the SI units, which is meter square. So 2.8 centimeter square is 2.8 times 10 to the minus 4 meter square. And then the wire area that we saw in the previous problem, it is 6.63 mm cube, mm square. And again, mm square I converted into meter square. So all these are now in SI units. 0 0.4 is dimensionless. Window area is in SI units in meter square, and wire area is also is in meter square. So you get the answer is 16.89 turns. But the number of turns has to be a whole number or integer number. So we will round it up to 17 turns. Yes, so centimeter square to meter square you can actually do. It has this 10 to the minus 4. You have to basically multiply. Similarly, if you want to convert from mm square to meter square, you have to multiply by 10 to the minus 6. You can find that out by yourself. But here you have to be careful that the AW that you use is based on the AWG. So the AW that we required was 6 mm, but once we selected the AWG, so that means AW is now 6.63. So you have to use this area, and you don't have to use 6 mm, but you have to use 6.63 mm. So to calculate the number of turns, you use 6.63, and WA is the for the core that we selected. The E-75 that we selected, that is 2.8 centimeter square is the window area of that core. And lastly, we have to now find the air gap uh, to get this inductance value. And we are told that the relative permeability is 2300, and you have to find the air gap in millimeters. So again, we use the formula of air gap that we saw uh, in the steps of the inductor design. We substitute all the values. Again, try to use SI so you don't get confused with different lengths. So the permeability of free space is 4 pi times 10 to the minus 7. This is the SI value. Then area is 3.37 centimeters square converted into meters square. Number of turns we saw was 17. Inductance is 60 micro. The path length was 10.7 centimeter. So converted into meter, it will be 10.7 times 10 to the minus 2. And then the relative permeability is given as 2300. So this is dimensionless, it is just 2300. And then you solve this, calculate this, you get 1.99 times 10 to the minus 3 meter. And since the question is asking about millimeter, we can convert it from meter to millimeter. So we get 1.99. So the answer to this last question, the air gap has to be 1.99 millimeter. So, and you can see that it is much less than the magnetic path length. The path length is 10.7 centimeter and the air gap is only around 2 millimeter. So that is what we meant by the air gap has to be very small compared to the path length. So these were all the problems that we had for today related to magnetics and inductor design. So if you have any questions related to these problems or uh, the magnetic portion, you can ask. You can ask in the chat or you can unmute and you can ask on the microphone. So as always, the recording of this session will be posted on YouTube and you will also have access to the slides. Yes, I think in your case, the questions they have asked for rounding off, because for example, here in this case, the window area was 2.799. So I think it would be good if you rounded off to 2.880. Yes, the RMS value. So basically, you have this kind of a current that is shown here. This is the inductor current, the shape of the inductor current. It has a DC portion and then it has a triangular AC portion. And if you find the RMS of this current, just you can do the integration yourself. If you do the integration, you will find that the expression for the RMS for this kind of a current, which has a DC value, and then on top of the DC you have an AC. This is the expression for the RMS. It is the DC portion, the square of the DC portion, plus the square of the peak to peak ripple divided by 12. And whole thing is in square root. And once we substitute the values here, the DC portion is 18, the AC portion is 0.4 amperes. If you substitute and you calculate this, you get that the value is 18.0004. And then you have to round off up to 2 decimal places. So basically you get 18.00 or 18 amperes. So the 0.4 is given in the question itself. So the current rating of the inductor is given as 18 amperes and the ripple limit is 0.4. Yeah, so 3.37 we did not, because we have to round off up to 2 decimal places. So if we had a third place that was given in the data, then we would round it off. So for example, if it was 3.377, then we would round it off to 3.38. Okay, so we have to round off up to the two decimal places. So that is why we did. Okay, so of the SI units, so if we start from the first for the magnetic field, so the current is obviously uh, in amperes is the SI unit. Number of turns is technically it's dimensionless. Uh, the length, SI unit of length is meter, SI unit of area is meter square, and similarly for any power it will be meter. The SI unit of magnetic field intensity H is amperes. We usually write ampere turns, but turns does not actually have an but so it is basically amperes. Uh, uh, mu mu r is dimensionless. Mu zero will basically have a dimension of h by b, or is it the other way around? So sorry, b is equal to mu h. So mu will be b by h. So b, the SI unit of magnetic flux density is Tesla, and then mu naught will be Tesla by amperes. Flux is basically Tesla times meter square, which is Weber. So it is called Weber. WB is the short form. And finally, flux linkage would be, I guess, it will also be Weber because N does not have a unit. So Weber turns is flux linkage. Inductance is given in Henrys. The SI unit for inductance is Henrys. So if you have all these terms in SI unit, you will get the inductances as in SI unit as Henrys. The rest, I think you should know. Voltage is just volts. MMF is ampere turns. Reluctance, I don't remember what is it called, but reluctance. If you just keep all these things in SI unit, so if you keep the lengths and area in meter and meter square, you should get the value in SI units. Uh, yeah, I think these are all the so the for here. So for the Steinmetz equation, you will get these values of K, M, and N for particular units. So whether it is milliwatt per centimeter cube or watt per meter cube, so that depends on these units, the values of K, M, and N, and they will be specified by the manufacturer. So the manufacturer will give you these the constants, and then they will specify that okay, so there is a this will you have to use in this equation, and the output power you will get in milliwatts per centimeter cube, and frequency has to be in kilohertz, and uh, flux density has to be in Tesla or some other value. So this equation, to use this equation, these parameters will be given for particular units, and they should be specified to you whether what are these units. And if they're not specified, then I think you should use SI, but you have to find out the specification. Uh, then for resistance, it is ohm. So all these things. So resistivity has to be in, I guess, ohm meter, and then resistance you will get in ohms. Power loss is watts. Yeah, I think these are all the terms that we have. Current density is currents per unit meter, so unit length, which is, sorry, length square, which is amperes per meter square, is the SI unit. So for temperature or temperature rise, technically temperature SI unit is Kelvin, but since Kelvin, the 1 degree Kelvin is equal to 1 degree, or the change in 1 degree Kelvin is equal to change in 1 degree centigrade. So you can use centigrade here as well. So you will get the value in centigrade. Yeah, so I think that is all the SI units. But if you have any further doubts or you get later on, you can Google it easily. This will you can find the answer in Google as well. So I hope that was helpful. If anybody has any more questions, you can ask. I will be here for sometimes. If other students they want to leave, they can leave as well. So to get the best use of this class, you actually have to uh, do the designs. So the best thing would be if you actually have an application you want to design a converter, and then you use all the lectures that you studied. You select the components, the semiconductor components. You select, you find the power loss. You select the heat sink. You select the inductors. I mean, that will be the best way to learn. But if you don't have those things available, then you just uh, do some examples, and solve and see what values are you getting, whether they are satisfying. But the best way would be to actually use this knowledge to actually design some converters. But the next best thing would be to solve all the examples, and uh, maybe maybe you can also do is, once you have gone through the whole course, you can select one converter for a particular rating, and you design the full converter from the semiconductors to the thermal management to the heat sink to the inductors, transformers, whatever you have, and maybe even the EMI filter as we'll study next, and even the PCB if you want. So that would be the best thing. So you apply all the knowledge that you gained from this course, and obviously to get a good grasp, it will take some time. Even one course will not be enough. You have to try. You have to see different. So, for example, if you select a device, so maybe you will miss something. There will be more loss than you anticipated. So you will learn from different things. So it will take some time to actually get a good grasp. But I think this course is a very good step in this direction. Okay, so if there are no more questions, then those who want to leave, they can leave. Uh, if you want to know, you can ask me in an email. I don't think uh, we need to uh, do this on this session. But basically, I'm a PhD student at IIT Delhi right now, and I'm working on this power electronics field. So if you want any more details, you can email me. I have given my email previously. I can give it again. If you need any help or you want to ask something, you can ask me in my email.